What I'm going to do is come back over here and we're going to do some live simulations. Now there's a few things that I agree totally with David. There's a few things that I'm going to question, believe it or not. And one of those is going to come back to here. Because when we looked at another alternative that Westgard was talking about with the QC selection grids, if we look only at the excellent method stability, he was saying when you use a rule for a method with a critical systematic error less than 2, for one control in a run, you would use a 1-2S rule, and I don't know if that's still a warning. And he's saying use a 1.25 or 1.2.5S with an N of 2. So the QC rules he's talking about here were an alternative, and you'll notice in the original grid he didn't have a 2.5 or a 3.5. So since that grid came out, there are a lot of other rules available to us. Now, just one little second here. If we go back down here, what we want to do with the live simulators is talk about how QC charts and rules protect patients. We'll do some real examples, and we'll talk about how QC charts and rules can fail to protect patients. And I'm hoping you find this remarkably interesting. What I have here is a simulator. This is something that you'll see as part of our online courses and so on, and I've used this extensively in the teaching because I found that if people can make the changes and see for themselves what happens when the mean changes or the SD changes or the assigned values change or the ranges change, when you can model these things in a safe situation and take your QC information and put it into something like this and say, what is happening? What would happen if there was a clinically significant shift? Before we answer that, I'd like to just expand on some of the things that David was saying about how QC rules work. Okay, I'm going to go through this first. We talk about the 4 key numbers of quality. There are 4 numbers that drive the quality of your method. If you know these 4 numbers, you can tell if your method meets quality goals, if it's meeting the clinical requirements you've set. You can tell, and you can tell from that what QC rules you would need to use to make sure you would detect a change if it changed from where you are now. Remember those 3 questions? Is my method okay? These four numbers will tell you, is my method okay? They will also tell you, how far can I shift? So is the method okay? Has it changed today? You would see a change on your QC chart. And the big question we're not answering yet is, would my QC rule detect it if it changed tomorrow? So I can come in here and say right now I'm using a 1-2S rule, and I'm shifting the mean by 0 SD. So with 0 change, just as David said, there's 1, 2, 3. So there's 1 result in 20. So there's 1 in 20 here, 1 in 20 here, 1 in 20 here, or 5%. Hang on, David, you said 10% with a 1-2S rule, and I'm saying 5. Can you clarify that?
I can. I work from the assumption that everybody is using 2 controls. Each of the controls, like you show here in Lab A, each single control has a 5% chance of being out, just like you said. But if you put 2 controls on, then each of them has the 5%. So you've got a total of 10% chance of one of the 2 being outside 2S on any run. If you run 10 tests at the same time, I say, then you've got a 100% chance on average that every run will have, every run of patients on those 10 analytes, you have virtually a 100% chance of getting a value outside 2S. If you move that up, as some people do in immunoassays or in hematology, and run 3 controls, then that number goes up to what? 3 times 5 is 15% 1 in 6 or 7 runs, you're going to get an outlier. It's guaranteed. So we're not arguing with each other. We're just talking about 1 versus 2.
I have an idea that out there a lot of people are saying, well, I know they say that in theory, but I don't see 5% of every run flagged, and I'm using a 1-2S. Just hold that thought, because we're going to answer that question. Why would you not see a 5% of your results flagged if you are using a 1-2S? So hold that thought. We're going to come back to it. If I haven't answered it well enough, ask it again at the end. What I want to do first is show you a little bit more about what David was saying about the rejection with the QC rules. So what this simulator lets me do is change the number of SDs that the mean is going to shift. So I can shift it here by 1 SD. When I shift it by 1 SD, the question you're really concerned about is not so much what's the probability of error detection or how many runs are flagged. The question that really concerns the patients is how many runs is it going to take you before you say this might be a problem? And I count 1, 2, 3, 4. And if you said, well, that's a 1-2S warning, I can ignore it, then 5, 6, I can ignore that one, 7, 8, 9, 10, I can go 19 or 20 runs without ever seeing this error. So let's say, and if we're not going to stop for the warnings, we're only going to stop for the rejects, right? So if I'm going to stop at a 1-3S reject, that's going to be 19 runs in. If I shift this by 2 SD, well, now I'm going to get a warning, then nothing, I'll ignore it, a warning, I'll ignore it, I can detect it in 4 runs. So a shift of 2 SD is detected much more quickly than a shift of 1 SD. If I shift it 3 SD, well, look at that, I'm going to get a flag in the very first run. And if I shift it 4 SD, every single run is absolutely flagged beyond a shadow of a doubt. You're going to get that reject in the first run. Now, lo and behold, you've heard people talk about 6 sigma. 6 sigma occurs when you can shift 4 SD before you're in trouble. That, folks, is not intuitive, and it's not explained well that I've ever seen in the sigma literature. So I talk about a margin for error. Margin for error is the number of SDs you can shift before too many results go outside allowable error. So it's how far you can shift before things go bad. So we saw here, as the shifts in the mean go up, the larger the shift in the mean, the easier it is and the faster it is to detect it. Now, we're going to take that and bring it back down again. So I'm going to leave okay. So we don't want to use a 1-2S rule. You can see that with a shift of 4 SDs, you get 2% or 5% false positives, just like what David was saying. But can is it necessary to use that 1-2S rule, because all of these results are way above 3 SD? So this is where we come over and go to the selection grids that we learned last week. So we're not going to look at the moderate or poor stability. That sort of has been taken out of the equation. But my critical systematic error, because that's what was measured way back then, so your margin for error is 4, your sigma is 6, your critical systematic error is 3.65. On these QC selection grids from 25 years ago, your choice was a 1-3.5S with an N of 2 or a 1-3S with an N of 1. So I'm going to come back here and say, okay, I can use a 3.5S. Well, looky there. Now I have 0 false positives. Hang on a second. So now these are outside 1-2S, but they're not flagged. Only things beyond the red lines are flagged. So this is where your red line is, sort of at 1-3.5S. I see questions. I'm going to go back to this here and back to the exercise we were doing. So we're going to check a 1-3S rule, 1-3.5S. Can I go to a 1-3S? Well, I come down to a 1-3S. I still have 0 false positives, and most of my results are flagged. What happens if I go to a 2.5S and I'm still shifting 4SD? Yes, I can manage that. And what if I go down, whoops, take it down to a 1.2S? So if I use the 1.2S, I get all these false positives. It looks like you can just go and use a 1.3S or a 1.3.5S. But why would we come down here to a 1.3S or a 1.2.5S? So let's see what happens. Go in and change this so that the mean beforehand is 103. So now my margin for error is 2.5. It can only move 2.5 SDs before it's in trouble. So the shift in the mean I'm going to simulate is 2.5 SDs. When there are 2.5 SDs that you have to detect before, see, my total error is 7 and it's allowed to be 12. So there are 2.5 SDs between where I am now and where I can go to. With only 2.5 SDs, I can use a 1.3S rule for n of 2 or a 1.2.5 for n of 1. So let me go to the 1.3S rule. Now what we've just heard is this shift of 3 standard deviations is significant. This would take you to the point that any further shift is going to be putting people, you've already got 2.5% of your people over the limit. If it goes any further than that, you're going to have more people over the limit. So this is the point that you really should be stopping when you're shifting the mean, when you shift it as far as you can, and you have 0 margin for error left, then that's what when you should stop. The 1.3S rule doesn't really cut it for me because you're still going to go 1, 2, 3, 4, 5 runs before you stop. When you can model it, you can see, oh, my other selection was a 1.2.5S rule. Well, now, if I'm using the 2.2S as well, I'm certainly going to see that change right away, and you should get those flags if you have your 1.2 or your 2.2S rule turned on. But the suggestion here was just to use a 1.2.5S rule. So if you use a 1.2.5S rule, that's when your line is drawn. Oh, sorry, this is the one. So is that fellow? That's right at 2.6. So you would actually see a warning on your first run. So the yellow ones are greater than 2 SD, and anything above the line is a reject. So this is your first reject signal here because it's outside 1.2.5. That's another reject, that's another reject. As you change your QC rules, your probability of error detection changes. So if I want to go down and use a 1.2S rule, well, then I would be absolutely sure of detecting this change, but I'm going to pay the price of the false positives. The question becomes, is it sometimes necessary to pay that price?